Hi, welcome to this video about Schlappi Engineering's three-body. First of all, I want to apologize for making this an extremely long video, but there's so much to talk about when it comes to three-body that it was almost impossible to make it shorter. I thought about doing separate videos, like separate chapters, but I chose to just make one long video just because every control and every VCO on three-body is so intertwined with everything that's going on in the module that, well, again, it's hard to split that up into distinct sections. Three-body is a really unique take on the complex VCO. It has 3 VCOs, where most complex VCOs only have 2. And its strength, and I don't think there's any weaknesses to it, is that it's completely digital. Well, it's a weird kind of digital. It's an FGPA, a logic-based circuit. And if you want to know what's that all about, you can watch a long video where Eric from Schlappi Engineering explains in a lot of detail what this means, how it works, and why he chose this kind of platform. The main strength of the fact that three-body is, well, not analog is not only 100% pitch stability and accuracy, it's also the fact that you can lock these 3 VCOs in pitch together, which makes it not only possible but just very easy to dial in clean and clear FM and phase modulation. Sounds like you can hear on old FM style synthesizers that usually just use phase modulation as well. Thanks a lot, by the way, to Eric and Jay from Schlappi Engineering for sending me this unit and for supporting this video. There won't be a separate segment of sound or patch examples at the start of the video like I usually do, simply because that would make the video even longer. I've uploaded a lot of patches to YouTube already, with detailed explanations about what I'm doing in those patches, and I'll try to make a playlist of those. You should be able to find that in the description box. You can expect a lot of sounds in the video though, as I'm constantly tweaking all the parameters on three-body to give you a taste of what it's all capable of. And I made a few segments where it's just sound and no talking to break up the constant barrage of me explaining everything there is to explain about this module. If you're just interested in one particular segment, please take a look at the chapter markers. They should make it possible to, well, jump around in the video for parts and pieces that you're curious about. Let's just get this video started. Before doing anything else, I want to outline which part of the module is associated with each VCO. It might be obvious, but, well, it might just as well not be obvious. It's all too often that these kinds of things are somewhat confusing. So let me add some markings to three-body so you can see what's what. The left VCO is pretty much a mirror image of the right VCO. There is a knob for the FM index. For the left VCO, this is normalized to the sine of the center VCO. And for the rightmost VCO, this is normalized to the cosine of the second or center VCO. There's an FM input. That's where the normalization from the center VCO goes. But since the jack is on the front panel, you can patch something in there coming from somewhere else or coming from Three Body itself. The thing you patch in there will act as a source for the FM, or as we will see later, the phase modulation. The FM index input jack next to it controls the amount of FM that's going on. When you turn the FM index knob, you kind of set this at a fixed point, but when you send something dynamic like, well, an envelope or an LFO or whatever really into the FM index input, you can modulate the amount of FM over time. There's a sync input as well for the left and the right VCO. And there's the volt per octave or ratio inputs. Here you send in CV. This can be regular bipolar CV or a pitch sequence coming from a sequencer. The outputs for the left and right VCOs are identical. There's a sine wave, a triangle, there's a saw wave and a square wave. And then there's these switches on the left. There's the type switch, there's the FM mode switch, and then there's the range switch. We'll go a lot deeper into what all of these do later in the video. The left and the right VCO also have a phase CV input. This has no index input, but there's just a phase input to which you can patch a source for the phase modulation, and you set the amount manually with the knob. For the left VCO, the source for the phase modulation is normalized to the sine wave of the right VCO, and for the third or right VCO, the source for this phase modulation is normalized to the sine of the first VCO. There's of course also the coarse and the fine tuning knobs, and these are used for tuning or for adjusting the ratio. The center VCO has a coarse and a fine tuning knob as well. Just below the fine tuning knob there's a knob for adjusting the amount of FM. The center VCO does not have an FM index input, and there's also nothing normalized to this input. So if you want to use FM for the center VCO, you need to patch something into the FM input, and then by turning up the FM CV knob, you adjust the amount that this signal frequency modulates the VCO. There's the phase 1 index and the phase 2 index knobs. The sources for this phase modulation are normalized. You can use sine 1, so the sine from the first VCO as a source, and you can use sine 3, which is the sine from the third VCO, as a source for phase modulation. But as you can see, there's phase 1 and phase 2 inputs on the bottom as well, and you can patch anything in there that you want to use as a source for phase modulation. The knobs, just like before, set the amount that this source will affect the phase of the center VCO. And since there's two of them, you can get really creative. And then there's also inputs for the phase 1 and phase 2 indices. Here you can send in a control voltage that controls the amount of phase modulation. And when you've connected something to these inputs, the knobs act as attenuators for the control voltage that you send into these inputs. The center VCO has a sync input as well. The center VCO has the same 3 switches as we see on the outer VCOs. There's just a little bit scattered across the panel. And then there's a separate volt per octave input for the center VCO as well. On the left there's one more input. You can see it's in use right now. It's the transpose input. And this is like a global volt per octave input for all 3 VCOs. I hope this really short panel overview helps in understanding what I will be talking about in the upcoming, well, minutes, hours, days maybe. There's quite a lot to figure out about three body with all the cross normalized stuff going on in this module. It's easy to get distracted by just crazy sounds. But let's try not to go into that territory. Let's walk you through what all these controls do first, because it can get quite confusing if you don't really understand what they are doing. And understanding what all of this does is also the best gateway to start making intentional sounds with three body. Right now we're listening to the rightmost VCO here, but we're looking at all three on the screen of data. I patched the triangle output of the first one to the first input on data, and this is the green line. The triangle output of the center VCO is patched to the second input on data. This is the blue line or blue trace. And the triangle output of the rightmost VCO, the one we are listening to, is patched to the third input on data, and this is the red trace. I've synced my scope to the third one for the moment, so that one is stable on the screen and the other ones are a little bit drifting. And this brings me to the first control that I want to talk to you about. You can see here on the top for the most outer VCOs, and for the center one it's here, a switch that allows you to switch between free running mode and ratio mode. Currently we're in free running mode, and this means that I can just tune all three VCOs independently. It doesn't matter what the others are doing. You can just tune these to your liking. In free mode there's a coarse tune knob and a fine tune knob. And in VCO mode you can go from very low to extremely high. Now, once you flick this switch into the ratio setting, you'll see something interesting happening. Let's do this for the left one as well, just for visual aid. And you can see it already for the green and the blue trace. These are now synced together, locked in phase as well. So this ratio setting syncs up the frequencies and the phases of the outer VCOs to the center VCO. Now, what's the center one syncing to when you flick this to the ratio switch? Well, at the moment nothing. For that you have to patch something into the VCO, but that's something that I will talk about later or in a later video about three body. So I'm telling you here that the frequencies and the phases of the outer VCOs are synced to the center one when we flick these to the ratio setting, but you can, well, see that it's not the case. And now this is simply because when we're in the ratio setting, the chords and the fine tuning knob become multipliers and divider for the frequency set by the center VCO. So if I turn this to the left, you can now see that all three VCOs are, well, perfectly synced. Let me unmute the blue trace coming from the center VCO for a moment. So now we're listening to the triangle output of the center one and the triangle output of the right one. Let's just ignore the left one for the moment. Now if I turn up this chords or mult knob, you'll see that we get frequencies that are multiples of each other. And these aren't just even multiples. All of the multiples are present. 2, 3, 4, 5, etc. So this is an harmonic series. The same goes for the division knob here, which was previously the fine-tune knob. This divides down the frequency of the right VCO compared to that of the center VCO. You can combine these. Imagine you want to do a multiple by 2, and then you want to divide it by 3. Well, that's entirely possible. And let's turn these knobs a little bit to hear what we can get out of this. Now all of this is very fun and dandy, but well, we don't want to be turning these knobs manually all the time. So luckily Eric implemented voltage control over this. In the free setting, the volt per octave input does exactly what you think it would do, but in the ratio setting, sending something into this input controls this dividing and multiplying. Now you have to choose which one it's controlling, and you do this with this bottom switch here. And for this you have to look at the words to the right here. Currently this switch is in the upper position, so it's on the mult setting, and this means that whatever you are sending into the volt per octave input will affect the multiplication of the frequencies. So I'm just using a manual offset here. So I'm controlling this with a signal going into the volt per octave input here. Now when this knob is completely to the left, Sending in any negative voltage doesn't make any difference. It's not like suddenly you will be dividing, but sending in a positive voltage, of course, creates these multiplications of the frequency. And if you turn this knob up, well, let's say just to the center, the voltage that you send in offsets this value, and sending in a negative voltage like I'm doing now offsets the value of this knob here to the left. Now, unsurprisingly, flicking this switch to the bottom position sets it to the division setting. This means that whatever signal you're sending into the volt per octave input here will adjust the divider. So let me send in positive CV signal. And the higher I go with my CV signal, the more the frequency gets divided. And the same logic applies. Whatever you are sending in is an offset for the value of this knob. So setting it to the center position and sending in a positive CV signal divides the frequency of this VCO even more. But then when I send in a negative signal, this knob is offsetted internally to the left. There's another thing that's important to watch out for in three body, and this is the function of the FM setting here. And you set this with this center switch here. In the lower position there's only linear FM, so whatever mode you are on, it doesn't matter. The FM will always be linear FM. But when you flick it to the upper position, well, it's important to know what setting you're in here. When we're in the free mode here, which we are currently not, everything associated with this knob, so the setting of this knob, this FM input, and also this FM index input, these will perform regular exponential FM like you're probably used to having in most VCOs. Now when we're on the ratio setting, this is no longer doing exponential FM, now it's doing phase modulation. So in ratio mode you have one regular phase CV knob and phase input here. There's no index input associated with the phase here. But you have an additional phase control under this knob, and phase modulation input and phase modulation index. And you might not know this, but when you do phase modulation of a VCO with another VCO that has the same frequency, you are actually performing some kind of wave folding. Now with all these ratio settings, you can really create interesting timbres with just this. And now you can start to hear that instead of just going ham on these knobs and turning them into chaos and noise territory immediately, it pays off to do things intentionally. So now I'm doing phase modulation on the right VCO. The source for this, as you can read below the big word, there is the cosine of the second VCO, so that means this output. But of course you can patch in any VCO or LFO in here. The amount of phase modulation, or well, in free mode exponential FM, is set by this knob, but you can also send in like, well, something else, an envelope for example, into this FM index knob, which means that you're automating the amount of phase modulation coming from the center VCO to the third one. Turning this knob down attenuates whatever you are sending in here. Turning it up, well, doesn't amplify whatever you are sending in, but lets it through completely. So what I'm sending in here is not actually doing the FM, it's just controlling the amount. It's like turning this knob, but there's something turning this knob for you. Well, that's what control voltage is usually used for anyway. So if I now again mute the other VCO, so we're just listening to the right one, and well, I wasn't planning on this, but let me just add some reverb. I think it might sound really cool, and maybe some stereo delay as well, why not? So if we sync the frequencies without doing any division or multiplication, we're just really wave folding. But I really like when it's divided a little bit. Let me just quickly patch a sequence into this input. Mind you, this is not controlling the core of the oscillator with the volt per octave signal. No, I'm just using a sequencer to control the ratio setting, and currently we're on the divider setting here. So my pitch sequence is controlling this knob here. And like I said, anything that you send in here is an offset for the position of this knob, or at least the value associated with it. And now if I unmute the other VCO again, you can get these cool intervals. Just a little bit of wave folding. Okay, let's turn down the effects so I can explain how the linear FM works on 3-body, and then I'll switch over to having this in free mode so I can explain how this knob here functions when it's free running, and then I will talk a little bit about the phase modulation here as well, which is independent of whatever setting you have of these switches. I changed around the tuning a little bit just to be able to demonstrate to you what the True Zero linear FM is doing. We are again just listening to the right VCO here, but I switched over to a saw wave so you can visualize a little bit better what True Zero linear FM is. And as you just saw me flick this switch for the FM mode into the bottom position, which says linear or lin, this knob here and everything that's associated with it is no longer doing the phase modulation, it's now doing the linear FM. So let's bring this up. The normalized source for this modulation is still cosine of the center VCO, but I set up the ratios in such a way that the center VCO is actually well, an LFO. But let me bring up the FM index, which is now controlling the amount of linear FM. And admittedly, this is not the most musical example, but I wanted to show you what True Zero linear FM does. And it's quite a bit different from regular exponential FM. And well, you can see that the wave, whenever the modulator goes below zero, maybe I should add a zero line here. So whenever this modulator, still coming from the center VCO, is going below zero, the saw wave of the right VCO is getting inverted. And this is really unique to True Zero FM. But let's change up the tuning again so we can listen to how this actually sounds at audio rates. So now that all three VCOs are running at audio rates, let me now bring up the FM index. Well, I think that speaks for itself. And since we're still in the ratio setting, right now all three VCOs run at the same frequency. And I don't think I mentioned it already, doing any kind of modulation, be it exponential or linear FM or phase modulation, with a modulator that has the same frequency or, well, at least a multiple or a division of the frequency of the carrier, gives really different results than just doing it with free running VCOs. I tried it with analog VCOs and it's almost impossible to get those really clear and sometimes clean sounding FM tones like the Yamaha DX7 or the Casio, what is it, CZ101? I'm not sure about that. But in fact they use phase modulation and no frequency modulation. Well, let me change the ratio a bit of the right VCO. think that's all really interesting. Now, instead of listening to a saw wave, which is already rich in harmonics, let's listen to and monitor the sine wave, and then let's try how linear FM sounds with this as a carrier. And while I've been using the built-in normalization, let me patch up a different modulator, because this can really change the sound. Let's try the square output of the center VCO. This follows the same frequency as the blue trace on data, and let's patch that into the FM input. So this is where you connect your modulator. Then if I turn up the index, you can see that this indeed sounds a little bit different. Let's try the saw wave. And just as before, I can send something like an envelope into the FM index input, kind of automate the movement of this knob. At some point, someone has to make a module with motorized knobs, so we can see this movement represented. Anyway, let's choose a looping envelope, and of course this knob now attenuates the CV signal that we're using to modulate the index. Let's remove the modulator. So we're once again using the normalized cosine of VCO2 as a modulator for the carrier, which is VCO3. I know VCO1 is on screen, but we're not listening to it, so you can really just ignore it. Let's play around with the ratio settings here. Let's zoom in a bit here. And by the way, these waves are still inverting, but because it is a sine wave, it is very hard to see. Let's patch up the saw output of the third VCO once again. Maybe I should zoom out a bit. If I slow it down, you can start seeing that we are indeed getting these inverted situations happening. Here it's a little bit clearer. Yeah, this is really great. I think this sounds really interesting. Let's go back to listening to... Let's go back to the triangle actually. And once again, I think this calls for a little bit of reverb. And when I say a little bit, I mean a lot. Maybe some delay. Now patch up a slow moving output coming from a chaos oscillator. I'm using Orbit 3 for this by Giovanni Audio Design. It's just like an LFO, but shapes are a little bit more chaotic. And let's patch this into the volt per octave input control of the center VCO. Let's turn on the frequency of this control voltage. To create a little bit of variation, you can just as well connect something to the ratio input of the right VCO. And as this switch is currently set to mult, this control voltage is now controlling the multiplication of the core frequency of the right VCO in reference to the center VCO, of course. I liked it more when it was controlling the actual pitch of the center VCO. I have to attenuate it again. Let's be a little bit creative with the timing of the envelope that I'm using as well. Let's listen to sine output. Be warned, this is going to be a little bit louder, not a lot though, but it's going to be 200% more doom metal. And then if you want, you can of course modulate the ratio at the same time as the frequency of the center VCO. And I'm really enjoying how this sounds, and don't forget, this is just one output of three body. We're just using the output of one VCO, and we're really just using one type of modulation, which is still just through zero linear FM at the moment. You can start combining different types of modulation. You can start to do cross modulation, which soon creates really interesting timbres. I think right now is maybe a good moment to, well, briefly explain what FM is compared to phase modulation. Because when you're just looking at the scope here, and even when we're listening, it's not always that clear what the difference between these two modulation techniques is. I made this animation, and to the top we can see what happens when a sine wave is getting frequency modulated. In a way, it's like taking the wave and squeezing it together and then stretching it apart. And depending on if you use an LFO or a VCO as a modulator, this squeezing and stretching is really fast or really slow. If you do this really slow, you're going to have some kind of vibrato, and it might be really obvious, but it's important to really keep in mind that in frequency modulation, you're actually modulating the frequency of your wave. The reason I'm saying this is, well, if you look at the example below, in this isolated situation, you can clearly see that here we are not stretching and squeezing the wave, we're just moving it from the left and the right. Of course, while this animated wave is not attached to anything, you can move it from the left to the right without limits. But when we're talking about a sound wave that is traveling through the air, or, well, a voltage that's oscillating inside your system, depending on how fast and how far the phase is modulated, you're going to get parts of the wave, and this is usually what we see on the scope, that get stretched and pulled apart as well. And if you do phase modulation at, well, exactly the right speed, not too slow, not too fast, you can also get a vibrato-like sound from it. But, well, it's just important to make the distinction that here we are not modulating the frequency of our sound wave, we're just modulating the phase. And it's a bit akin to the Doppler effect. It's not completely correct to make this analogy, but I think it serves a purpose. So when an ambulance is driving past you, the siren is, well, usually it's a sound that's getting frequency modulated anyway, but you can hear an apparent pitch rise as the ambulance gets closer, and then when it's past you and starts driving away from you, well, and that's only the case if they're not coming for you, of course. So let's hope it drives away, but as you know, this has happened dozens of times in everyone's life. When it drives past us, the pitch apparently drops. Well, of course, if you are in the ambulance, there is no pitch fluctuation to the sound apart from the inherent pattern of the siren. But then there's another really weird duck in the pond, and that's the through zero FM. In through zero FM, we're also modulating the frequency. So that's just like exponential FM and, well, your fault productive input. But with through zero, and it's usually the linear FM that's getting implemented in such a way that you can get it to go through zero. Whenever your modulator drops below zero, your carrier gets slowed down so much that it at some point actually stalls, so stops oscillating. At that point it can be just a flat line, but when the voltage of your modulator drops further below zero, so going into the negative part of the voltage range, your carrier starts rising in frequency again, but it will be inverted. I found it really hard to animate this. Well, I'm not really using animation software anyway, but I'm sure you will sort of understand what I'm talking about. See, this already took longer than I was planning to talk about all of this. But let's play around with this patch for another minute or so, and then we'll take a look at this right VCO when it's in the free setting. As long as these two outer VCOs are in the ratio setting, they keep track of the frequency of the center VCO. So if you have them tuned into an interval like this, using the divider and multiply knobs, and you change the pitch of the center VCO, then all of them move together and the intervals stay the same. Or at least the musical relationship between the notes stays the same. If you then want Three Body to play a sequence, it's sufficient to send in a sequence or anything really into the center VCO's volt per octave input. And then repitching the center VCO changes everything together. By the way, you could achieve the same effect by sending something into the global transpose input. But let's stick to the volt per octave input here. Now all of this behavior changes when you flick these top switches into the free setting. So let's do that right now. Now you can hear that the center VCO, which is the blue triangle, is playing the sequence just like before, but the two outer ones, which are now square waves, are quite annoyingly droning away. And when you now move the coarse and the fine tuning knob, we just change the frequency completely independent from the center VCO. This of course doesn't mean that you cannot get them to move together. For that we should just use the transpose input, which is, like I said before, kind of a global pitch control. Changing the pitch of the center VCO at this point only changes the pitch of that center VCO, which is probably pretty obvious at this point, but well, doesn't hurt to repeat some things. Of course, you can send in a pitch sequence separately to the outer VCOs just as well. So now just the right VCO is getting pitch information and the other two are just droning away. Let me sync the scope to the third VCO. And if you have a polyphonic sequencer or something like a shift register to distribute different notes to the different VCOs, well, then you can use three body for great sounding chords. And of course you can still introduce all this kind of modulation. Okay, so right now we're listening to only the red VCO, which is the right one, and I'm still using the square output. Let's use the triangle output instead. The center switch here is still on the linear FM setting, so let's keep it there. And let's now introduce some through zero linear FM coming from cosine 2, which is this output here, to the right VCO. Now there's several functions that I haven't mentioned yet, but one of them is the bottom switch here. When an oscillator is in free running mode, then this switch selects between high or audio rates and low or LFO rates. We have the same kind of switch here for the center VCO, and this means that we can, when we flick this to the LFO setting, use the cosine LFO to modulate the frequency. And now you can freely play around with the relative tunings. To find a setting that you like. Let's crank this modulation up to extremes. And let's see if we can visualize the through zero behavior better with a saw wave. We can. Let's flick this switch in the upper position. So the center VCO is running at audio rates. By the way, everything else that's associated with this knob acts exactly the same as before. You can send anything into the FM input here to use as a modulator, and you can send anything you want into the FM index, which will modulate the amount of frequency modulation. Now let's set this switch in the up position, which changes the FM behavior from linear through zero FM to regular exponential FM. And the source, when we leave this jack unplugged, is of course still the cosine of the center VCO. Actually, I should patch up this cosine to the scope so we can exactly see what signal is modulating the saw wave of the right VCO. So this is regular exponential FM, like you can find on most VCOs. Now let's flick the switch back to the bottom position for a moment so we can, well, compare these two types of FM. So you can see on similar settings we get really different results. Let's monitor the triangle output once again. We haven't talked at all about the bottom phase CV knobs and inputs, but these, well, behave exactly the same as the phase modulation that we talked about when the oscillators are in ratio mode and this switches in the upper position. It's just that they have their dedicated knobs. In this mode you cannot change. This is always going to do phase modulation. The big difference here is the normalization. So this phase CV, the phase is getting modulated by the normalized connection from sine 1. That's this trace here. And for the left one, it's the mirrored situation where the source for the phase modulation is the sine of the third VCO. You can patch in your own signal here to use as a source for phase modulation. But keep in mind, if you want to address the amount of phase modulation, you either need to manually turn this knob, or you should connect something here that's running through a VCA with, well, an envelope modulating the amplitude. By the way, let me connect manual offset to the phase CV input. Let me briefly switch over back to ratio setting. And I'm doing this quickly just to show you that when I send like 5 volts into the phase CV input, then you can see what phase modulation is actually doing. It's just changing the, well, horizontal position of the wave. And if you do this really fast, I'm moving my whole case here too fast and it will start sounding like timbre modulation. Too slow and you're not going to hear anything change. But if you do this at the right speed, you perceive a frequency change, while there really technically isn't. Okay, back to free mode. Now all oscillators are back in free mode, because I want to explain to you how the sync input works. But first I want to show you why I think sync is great. And it's one of those tools that, well, we should all use a little bit more often. So both outer VCOs are synced to the center one. I used the sine output to sync the left one, and I used the cosine output to sync the right one. There's a lot of VCOs around that only accept square waves into their sync inputs. Well, and to me that's always a little bit disappointing, but it's safe to say that three-body syncs just nice to just about everything that you send in, as long as there's a little bit of amplitude to the signal, of course. So we're listening to all 3 oscillators, and I left the center one centered on the mixer, and the outer ones are band left and right. I'm using the sine outputs from both VCOs, which you can see when I unplug these sync cables. and I'm using the saw output from the center one to monitor. Well, I can just as well explain how sync works at the same time as showing you why I think it's great. So when you send something into the sync input of an oscillator, its oscillations get resetted, so they start over whenever it detects a zero crossing a rising edge usually. In practice, this means that whenever the oscillations that I'm using here as a master are going up, so if they're doing this, whenever there's going up across the zero line, this is detected by the sync circuit, and this causes the slaved oscillator, so the outer ones are the slaves right now. This causes the slaved oscillator to start over. And if I zoom out a little bit here, you should be able to see this. Let's remove this sequence. And in sync, well, it's in the word. The pitch of the slaved oscillator doesn't really matter because it's getting synced by a master oscillator. But if you start changing or automating, modulating I should say, the tuning, you'll hear that we are, well, getting a timbral change. Now in sync it's important not to go up too high with your slave oscillator, or the sync will have, well, little to no effect. And this is normal. As soon as you have enough oscillations going on between the oscillations of the master VCO, you're not going to hear these little resets. When you, well, keep it somewhere in the middle, you can get awesome sounds. If you go too low with the pitch of your slave oscillator, you can see that there's almost no oscillations left, because the wave is moving so slow, it's getting nowhere, and then it's already getting resetted. So let's keep it here somewhere, and then when I change the pitch of my master VCO, the absolute pitches of these slave oscillators isn't really changing, but they are getting synced to the center one, resulting in different timbres for every note. Then of course, if you start modulating parameters of your VCO, and in three body this is really easy. You can find these broken sounds really quickly. Let me first show you how you can do it a little bit more subtle. So I'll send in a slow LFO to the FM inputs of the slave oscillators. And And if I bring up the index, you'll see that the slow LFOs that I'm sending in here cause these interesting timbre changes. And if you bring it up a lot, this is of course much more noticeable. You can just use the normalized FM, of course. And by the way, I'm on the linear FM setting right now for the outer VCOs. Let's just start doing some cross modulation here. And if I then introduce the LFO to modulate the frequency of my outer VCOs, once again, you can get really great stereo sounds from Three Body. And as you can see, well, I hope that you can still see this. These knobs for the modulation are, well, they're not even a quarter up. Let me turn them up halfway. Yeah, I think that's really great. So this is just using the internal cross modulation. Right now it's the phase parameter that's getting cross-modulated between the outer VCOs, and I'm using an LFO to modulate the pitches of these outer VCOs. If I remove the sync cables, well, the mayhem is still there, but it's a lot less musical. Well, again, it's in the word sync, but you can really hear when I reconnected those cables that these noisy signals that we have left and right, that they really lock in pitch. You can also see and hear that sync is a great tool to introduce a little bit of grit into otherwise very clean oscillations. By the way, if you are in ratio mode, we already talked about this. If you're in ratio mode, for the outer VCOs, the frequencies get synced to the center VCO, but you can send in something else into the sync input as well, which then takes over the role as a master to create these perfect multiples or divisions of the harmonic series. Let's take a signal from another VCO. Let's tune it up a little bit. You can see that everything is, well, unsynced. But if I now connect the same sine, and well, let me first melt this. If I connect this sine to the sync input, you can see that we have, well, the same situation as we had before, but now the right VCO of 3-body is just, well, synced in ratio mode to an external VCO, and this is, well, really exciting. So if I change the tuning of my external VCO, three-body follows just perfectly. And you can of course do the same thing for the left VCO. So right now the left one, let me unmute it. The left one is still in free running mode, as you can see. This is completely different behavior. Let me change the tuning of my external VCO, which is now the blue one. You can see how different they behave, because one is on free mode and the right one, the red one on the scope, is on ratio mode. But let's flick the left one into the ratio mode as well. That's a nice harmony. I'm going to pan these to the left and the right again. So currently the center VCO is not being used. So let's flick this to low. So it's running at LFO rates. And now you can use this one to start doing all kinds of modulation. So we're still on the linear FM setting. For the outer VCOs, let's switch these switches to the phase modulation setting. And then it's much easier to dial in some apparent vibrato, even with unattenuated signals. Because, I mean, when we switch to FM, it's really hard to dial in just a little bit of vibrato. Well, it's nearly impossible. And well, if you kind of abuse or misuse phase modulation, you can get this kind of thing happening. Let me fetch another cable here. I hope it's not a cable of 3 meters. No, it's not. Let me once again make some music with this. So right now I'll have a pitch sequence, but I won't be connecting it to Three Body. But I'm just going to connect this sequence to my external VCO, which is now, well, kind of a master for everything. Let's tune it down a bit. Let's increase the speed of our vibrato. Well, and let's now switch over to the free setting, which will cause these outer VCOs not to be, well, frequency synced or ratio locked, as I call it, but then they will just, well, hard sync. And then, of course, we're no longer doing phase modulation, but we're doing exponential FM. Let's turn these up. And now let's introduce some cross-phase modulation between the outer VCOs. Let's play around with the tuning of our external VCO. And if we go back to audio rates for the center VCO, we get this kind of thing, well, which is just awesome. But let's dial it back a little bit. I'm sure there's a few people screaming at their screens right now. Don't turn it down, turn it up. Okay. It's been a long video, but we're getting to the end of it. We're not quite done yet, though. In the next segment I want to, well, I always say briefly, but it's never briefly. I want to tell you a little bit about the things that are unique about the center VCO and especially its outputs. I also want to talk a little bit about the headers on the back of Three Body that let you change a little bit of how it behaves. And I think then we're just about done. I changed up my routing here a little bit so I can show you what's unique about the center VCO on Three Body. I've patched the sine and cosine outputs of the center VCO into data. Don't mind the first input here. I'm just using the square wave of the center VCO to clock or to sync my oscilloscope. For the most part, the center VCO on Three Body is pretty much the same as the outer VCOs. But of course, there's, as you can see from the panel itself, there's a few differences. First of all, instead of one phase input and knob for each VCO, the center VCO has two. There's one normalized to the sine of VCO1 and one of the phase modulation knobs and inputs are normalized to the sine of the third VCO. That's this one here. There's also phase index inputs associated with this with these parameters, so you can modulate the amount of modulation that you set with this knob, well, and this one here as well. There is an FM input as well with a knob for attenuating anything that you send in here, but there's no separate FM index input like on the outer VCOs. There's also nothing normalized to this input, so if you want to do FM for the center VCO, you really need to patch something into the FM input here. Apart from these things, you have the same exact control scheme as the outer VCOs. There's a knob for setting the type of, well, tracking. It can be free running like it is now. Then you use the volt per octave input just like you would expect that you use it. There's the ratio setting, which means the volt per octave input turns into the ratio modulation input. For the center VCO to produce any oscillations in ratio mode, you have to send in something to the sync input. Where is it? It's here. And then it will track the pitch of an external VCO. Then you can adjust the ratio with the coarse and fine knobs. You have a switch here to set the center VCO to low mode, so then it becomes an LFO. When you're on the ratio mode, this switches between modulating the multiplier or multiplying the divider. We have the same options here when it comes to choosing what the FM input does. On the top setting of the switch, we have exponential FM when we're in free running mode. When we are in ratio mode, this is phase modulation, so that means that the FM input will be used for phase modulation. And when we set this to the bottom position, we just have linear FM. which is just like on the outer VCOs through 0 linear FM, and this applies to both the free and the ratio modes. Now, well, to me, what's most unique about the center VCO is that you have a few extra options when it comes to outputs. Not only is there the sine, triangle, saw and square outputs like we have on the outer VCOs, the sine also has a cosine counterpart, and that's what we're seeing on the scope right now. And as you can see, sine and cosine are not the inverted versions of each other. They are not 180 degrees out of phase. These waves are 90 degrees out of phase. So even when you listen to them just mixed in mono, you don't get complete cancellation, and you still hear something. It would be different when these would be 180 degrees out of phase, then you simply wouldn't hear anything when you mix them in mono. Speaking about mono, let's listen to these in stereo. So I'll pan the blue trace, which is the sine output, to the left, and I'll pan the red trace, which is the cosine output, to the right. And this, well, depending on how you're monitoring this video, should already give you quite an interesting stereo spread. And there's the same situation for the saw and, well, a second output, which is called cosaw. I know Eric once stated in a video that cosaw really isn't a scientific accurate name, i.e. it simply doesn't exist, but, well, it's an easy way to explain what's coming out of this output. So again, these waves are not 180 degrees out of phase, they are just 90 degrees out of phase, which produces an interesting stereo image when you pan them left and right. Let's go back to sine waves, simply because they're a little bit less harsh on the ears. And I can't possibly cover the center VCO of Three Body without talking about the headers on the back of Three Body. There's quite a few of them that let you make choices about the behavior of Three Body. And one of the things that you can choose is whether the phase modulation for these, let me call them twin outputs, if the phase modulation is going in the same direction or if it's going in the opposite direction. Now, if that doesn't mean anything, let me show you. I'm sending in 5 volts here. So it's not an oscillating signal, it's just 5 volts of DC offset or 5 volts of bias, if you will. And if I now turn up this knob, I will let through this signal to the phase modulation circuit, and then you will see that the waves here move horizontally, just like you would expect with phase modulation, but they move in opposite directions. And the same applies to this phase knob and everything that's associated with it. And of course, this is amazing if you want to create cool stereo effects. Let me use the right VCO here as an LFO. By the way, I haven't talked about this, but you can see the behavior of these VCOs represented in these LEDs. For the right one, we can clearly see how this oscillates between positive and negative. We also can see its frequency. And when the LEDs are kind of purple, well, this just means that they're oscillating between red and blue very fast. So we just see it as purple. So if I now connect the sine output of the right LFO to the phase modulation input on the center VCO. You can see and hear the magic that's happening here. Let's monitor the saw and co-saw outputs. Let's increase the rate of the LFO. And if you really turn this down really slow, and we have a really subtle stereo movement. And if I recenter my VCOs, so they are not panned left and right anymore, you can hear this phase, well, I don't know really how to call it, but you can hear how the phases of these two waves start interacting with each other in interesting ways. You can of course still use the other modulation inputs, like second phase input here. Or the FM input. Which is causing really interesting results because the left VCO is ratio locked to the center one. Let me pan these waves left and right again. Left and right. So let's send an external VCO into second phase modulation input here. And I think you can hear how this can create awesome and interesting stereo sounds just from one VCO. Let's go back to the sine and cosine output. And this bubbling or beating effect is just caused by the interaction of all the modulation that's going on here. Because I'm really just sending in just a VCO with a steady pitch here. Really cool, Eric. Really cool. Let's remove this. Let me center these on the mixer again. And now you can see or hear that we're getting some cancellation. So once again, I've connected the static DC, so 5 volt is going in to the phase input here. And if you don't like the behavior of these sine and cosine or saw and co-saw outputs moving in opposite directions, you can change this by placing a header onto the back of the unit. There's quite detailed information about this in the manual of Three Body. It's really worth a read. There's a lot of cool patch examples in there and suggestions that should make you think a little bit, which is always a good thing. So if you don't like this behavior, you can change it. Something else that you can change has to do with the square output. The square output follows the phase modulation of the sine and saw outputs, so it goes in the same direction. But if you don't want the square wave to be affected at all by the phase modulation, you can also adjust this by changing the headers on the back of Three Body. You can see I didn't really know this before I tried. The triangle wave is also affected by the phase modulation, but it's going in the opposite direction of the sine and the saw outputs. Anyway, there's another header on the back that lets you change the sync or ratio mode. Normally when you sync these outputs to each other, like we're seeing here, the green square here is the output of the left VCO, which is in ratio lock mode. So normally this ratio lock mode, as I call it, just tracks the pitch, the frequency of either the center VCO or whatever you send into the sync input, but it can track pitch and phase at the same time, which is kind of a phase locked loop circuit that takes care of this. But if you really need the phases to align, you can make Three Body do that for you by changing one of the headers on the back. There's another header that has something to do with the modulation inputs for FM. You can tame the high frequencies of the signal that you send in here, which changes the behavior of the FM a little bit and the sound as well. And then there's a header for a possible future expander, but the chances of an expander collapsing into existence are really, really infinitesimally small. Well, I think the feature set on Three Body is already rather complete. I mean, there's so much that you can do with this module. I think that we finally have reached the end of the video. There's still so much that I would want to tell you about my experiences with this module, or just interesting patches or ideas. The video is already way long, so I'm sure if you dig around on my channel, well, I try to make a playlist and link that in the description box with all kinds of different patches that I made with Three Body over the past months. There's quite a few of them, and there's usually some kind of explanation about what's going on, what I'm doing in the video to produce the sound that's coming out of Three Body. If there's any questions, please leave them in the comments. There's probably something that I forgot to mention, but hey, it's been a couple of long days getting this video recorded and edited. I really hope you learned something about Three Body and maybe about synthesis in general. Thank you very much for sitting through this video. See you next time. Bye.